The co-director is Dr. Roland Thorpe, and Dr. Joe Gallo will be here. They are going to be a bit late today, but they will be joining us, and hopefully some other people will be joining as well. So we are very pleased today to have a guest speaker, Dr. Chinli Zhu, who's I think well known to many of you, and I will turn the mic over to Amal Wanakatunga, who is going to introduce Dr. Zhu.
Hi, everybody. Yeah, I get the pleasure of introducing Chinli. So he is an associate professor of medicine in the Department of Medicine, Division of Geriatric Medicine and Gerontology here at the Johns Hopkins University School of Medicine. Dr. Xu currently serves as the division director of biostats and holds joint appointments in departments of biostats and epi. He's also the founding member of the Johns Hopkins Center on Aging and Health. He completed his doctoral training in biostatistics at the Johns Hopkins School of Public Health in 2001. And his scientific research centers on the understanding of the natural progression of physical frailty, with a special emphasis on measurement and research measures to uncover the intricate relationship between physical frailty and cognitive decline. And also, Dr. Xu is a fellow of the Gerontological Society of America. And, you know, when I first met Chinli, it was just immediately clear he has this gift of explaining complicated topics in very simple ways. I think he's one of the rare biostatisticians that I've had the pleasure of receiving mentorship and guidance from, who can really delve into the science and very complicated relationships and speak to these as deeply as he can speak to study design and statistics. So I think it's a real treat to have him here to speak with us on this topic of missing data in longitudinal data sets. So with that, Chinli, I'll let you take it away.
Yeah, thank you, Amal, and well, we'll see if I can do the effective communication today. Thanks for attending the session. So I'm going to share my screen. All right. So my topic today is dealing with the missing data in longitudinal data sets. It is really a big topic. I mean, but today my goal is to introduce the concept of missing data and focusing on these different types of missing data and their likely impact on statistical inference. And also I'll be talking about some analytic approaches commonly used to handle missing data in the longitudinal data analysis setting. And in conclusion, I'll provide some general guidelines for good practice with missing data. So why is missing data a special problem in research on aging? I think I don't need to preach the choir here. I mean, you all have had experience with working with older adults, and some of them are highly vulnerable. And because of that, they are at high risk of, experiencing adverse health outcomes that may preclude them from participating in your study. So certainly mortality is the one of the leading causes of dropout and study attrition, but you also could experience disability onset, acute illness that interfere with participation, including a refusal and dropout or unable to do a particular task, such as walking 4 meters. So now the consequences of missing data, they can lead to biased estimates and incorrect conclusions. And, if you are aiming to, derive generalized findings from your study population, missing data certainly can, affect the generalizability. And from a statistical standpoint, I mean, even though that, a particular analysis may not bias the estimates, right? It can reduce statistical power because of reduced sample size due to missing data. So what can we do? What are the options, when we are analyzing longitudinal data with missing observations? I mean, the naive approach that for us to do is to just ignore it, right? So this is called a complete case analysis. Basically, just delete any of the records with incomplete observations on covariates or on the outcomes in your study. Or we can do better, right? To try to get a handle on the missing data bias, by using something like inverse probability weighting or IPW. The idea is to weight the non-missing observations, to make them more representative of the study, the entire population, including those with missing data. So I'll come back to some details about the IPW in a few slides. And the third approach is a missing data imputation, which is becoming more popular. The idea is to create multiple plausible values for missing data based on observed data and certain assumptions about how data came to missing. And then once you have generated the complete data sets using these plausible values, and then you just conduct the conventional analyses for each complete data set. Now, the last step is important. So after you have run multiple analyses using multiple data sets, you need to find a way to combine the results, the parameter estimates from the different analyses of the different data sets. So in that process, what you are aiming to do from a statistical standpoint is try to get at how to correctly account for the uncertainty in the imputed values, so that in order to get a valid inference. The last approach, but not the least, is called a likelihood-based approach, and which is a method that try to concurrently model missingness, and along with the main model for the scientific question of interest. So there is a combination of modeling the missingness process, but also model the outcome of interest in a single step. Now, the validity of each depends on the missing data mechanism. So what that means is, the degree to which the missing data stand to bias a given analysis, depending on the analytic method we use, the degree to which that observed data represent those in the target population. And to address the latter, knowledge of a process that lead to missing value is important. So this process has been codified by Rubin in 1976 as the missing data mechanism. So in Rubin's original work, he classified missing data mechanisms into three classes. The first one is called a missing completely at random, or MCAR. What that means is, the missingness is independent of both the observed and unobserved measurement. Okay, so the unobserved word is actually very important. So if you have a missing completely at random, then whatever you observe should fully represent the target population. Okay, so that's the essence of missing completely at random. The second class of missing data mechanism is called a missing at random. So it's a sort of a step down version of the MCAR in the sense that now the missing data the likelihood of having missing data is related to the observed information you collect in your study, whether it is age, gender, socioeconomic status, or baseline health status. So that's the key. If you believe that the missingness, the likelihood of missingness actually depends on the observed data already collected in the study, then you have a situation called missing at random. So now the third is the most challenging of the three, is called missing not at random, or MNAR. So under that scenario, the missing may depend on the missing value itself, right? So this is the most difficult to examine because because you don't observe, right, the missing value. So how can you know that the likelihood of missing has to do with the missing value itself? So that remains to be the most challenging scenario in statistical treatment of missing data. What we can do at the present time is to do a sensitivity analysis by making different assumptions about how data came to missing, but see how the results vary depending on the assumption that you're making. Now, the last bullet, it's just a recap that, in order to assess these assumptions and determine which missing data mechanism is most reasonable, it depends on the specific mechanisms. For example, if you want to see whether the data are actually missing completely at random, so that's something you can do, by doing the exploratory analyses, compare the characteristics of those who were in the study or versus those who were not in the study, and to see if there are systematic differences in those characteristics. If the answer is yes, then you can pretty much sure that the missing completely at random scenario does not work. But for the other two, the MAR and MNAR, the observed data cannot provide you a definitive answer. So in order to illustrate the different missing data mechanism, I want to show you just a very simple example. So here we're looking at the relationship between the gaze speed on the y-axis and the leg strength on the x-axis. And the dots represent individual observations, and then the green curve represents just a trend line. So in this case, we'll only worry about missing outcome, which is gaze speed. So just for simplicity, here we're assuming the leg strength is fully observed. Now, if you have missing data, which is indicated here by the orange dots, right? But you see the distribution of the orange dots, it's pretty even, both in the x-axis and the y-axis. Okay, so this is an indication that maybe this is a scenario where the data is missing completely at random. For example, maybe during the study, there's some random power outage, right? Which, affected the data collection of certain outcomes, such as, electronic measurement of leg strength, for example. So under this scenario, if you do a complete case analysis, that will give you unbiased estimates of the relationship, but you'll get a suboptimal statistical power because of the missing observations. Now, if you do these other fancier approaches like IPW and the multiple imputation and the log likelihood models, you'll also get unbiased estimates. But the advantage of using these other methods is to gain statistical efficiency, so you can have a smaller standard errors if you are willing to go that extra step to account for the missing data in your analysis. So now the other way, to illustrate the missing completely at random is you compare your observed distribution to an expected distribution, sort of happens in ideal setting where there's no missing data. So in this case, you compare the box plot of the distribution for the outcome and for covariates between the observed and expected, you don't see any systematic differences between the observed and expected. So that's the scenario is for the missing completely at random. Now, the second missing data mechanism is called a missing data missing at random. So here, again, we're looking at the same relationship between the two. But if you look at the orange dots, now the orange dots actually seems to be is at the lower range of leg strength or lower range of gait speed, right? So that means that the likelihood of observing gait speed depends on the leg strength. You know, for those who have a weak leg strength, the likelihood of having missing walking test is greater. So in this case, depending on what you are trying to estimate, for example, if the goal of the analysis, part of the goal is to estimate the population average gait speed in your population, because of the missing data, in this scenario, you may be underestimating the population average of your outcome, right? So now look at the box plots again. You know, again, if you're comparing the observed versus expected, in this case, you'll see that the observed had a higher leg strength on average compared to the expected. Similarly, the gait speed will be having a higher gait speed compared to the expected. So in this scenario, if you conduct the complete case analysis, now you'll get a biased inference. And so it is important, if you have this situation, you need to do these other choices, you know, the IPW, the MI, and the likelihood approach, which will provide unbiased estimates. So the last scenario is called a missing not at random. So in this case, actually, the observed information cannot help you predict the missing data likelihood or the value of the missing outcome. So for example, if you are trying to measure the gait speed among those who are not using walking aids, right? Not in wheelchair, not using canes, you know. So in that case, basically you are implicitly, you know, designing a cutoff value on the gait speed, below which that the gait speed test would not be administered, right? So there is anything below the red dotted line, you will not be observed on the outcome. So in this case, if you can imagine that if you get rid of any outcome values below the dashed line, then fit the regression line, this line, blue line, will look very different from the true line, which is the green line, right? So in this case, you know, you'll get biased inference regardless of which method you use. You know, if you do the complete case analysis or you're doing the inverse probability weighting, multiple imputation, all those methods will lead to biased estimates. So what you need to do in this scenario is you'll have to model the missing data mechanism. So I'll come back to this last point in a few minutes. So now you may have heard this distinction between the ignorable and non-ignorable missing data. Okay, so the issue of ignorability pertains to a statistical consideration. You know, in making the statistical inference of whether it matters to consider or you can ignore the missing data. In reality, I mean, you just cannot ignore missing data, right? So I just wanted to say that up front that the ignorability has to do with the statistical inference. Now, whether it's ignorable or non-ignorable depends on the missing data mechanisms I just reviewed, and also depending on which analytical model you're using, and also in some cases depends on whether you are analyzing missing outcome or you are, analyzing missing covariates. If the data are missing completely at random, then it's ignorable from a statistical standpoint. And if it's MAR, and you also are using a maximum likelihood estimator, like a random effects models, for example, then it is still ignorable. Ignorable in the sense that it's not going to give you biased estimates of parameter estimates. Okay, so let's briefly talk about the different approaches that you can use to handle missing data. So these are the general approaches can be applied to both cross-sectional analyses and the longitudinal analyses. So first, they call the inverse probability weighting. So the idea is to conduct a complete case analysis, but you are assigning greater weight to an observed complete case with higher likelihood of missingness. So in order to create these weights, the first step you need to do is do a modeling of the likelihood of missing data. Or specifically, you will be modeling the probability of being complete. Okay, so for example, you can take a logistic regression model, and for a missing data indicator, R equals to 1 if it's observed, 0 if it's not observed. And then you need to add a covariates in the model. Those covariates are supposed to be related to the likelihood of missing data, or could be related to the values of the study outcomes. So the purpose of that model is to predict the likelihood of missingness. So then once you have the model and getting the estimated probabilities of being observed or being complete, and you use those probabilities as weights in the complete case analysis. So the validity of this approach critically depends on data missing at random, meaning that the likelihood of missingness can be explained by the data that you have already observed. I'll come back to this issue about the relationship between the IPW and the multiple imputation later. You can stop me if you have any questions. Now, the next alternative approach is called a missing data imputation. Underneath that, you have two choices. You can do either single imputation, which means that each missing value is filled in with only one plausible value. You can use like a simple average as the imputed value for the missing data. Or you can do last observation carry forward if you are in the longitudinal data setting. The pros about single imputation is it's simple and it's straightforward. The cons is you'll produce a biased inference. For example, that basically you are ignoring the uncertainty in the imputed values, which can lead to overestimation of statistical significance. But single imputation is useful if you have only a small amount of missing data in your study. Now, a better approach is for the multiple imputation. So here you are incorporating the uncertainty in the missing data into your modeling, by producing multiple values to replace the missing value. And then you conduct analyses on every imputed data set using just a conventional approach. So suppose that you impute each missing value with 10, values, and then in that case, you will produce 10 data sets, right? So what you need to do next is to conduct a regular analysis for each of the 10 data sets. Then once you have finished fitting those models for each data set, you need to statistically combine your analyses estimates, model estimates into your final parameter estimates. So in order to account for the uncertainty in the imputed values. So the key assumption underlying both the single and the multiple imputation is the MAR or MCAR. And it is important to point out that the multiple imputation is generally more efficient compared to the inverse probability weighting approach, because it uses all the data that is available. And so more efficient is in terms of getting smaller standard errors and greater statistical significance, potentially. And the other thing is to comment on is that the multiple imputation also allows you to incorporate auxiliary variables, which can result in improvement in the efficiency and bias reduction of the main analyses. So one example of auxiliary variable is, for example, the duration between assessments, or the survey modality, right? It could be by phone or by online, or survey completion time. If you believe that those characteristics somehow affecting the likelihood of missing data, so you want to make sure that those kinds of information are incorporated into the missing imputation model. So in terms of steps, which I already said it, I mean, the step one for the multiple imputation is to, you need to create a multiple plausible values of a given variable and then use those values to substitute the missing value. Then you conduct a standard analysis for each data set. After imputation, then the results needs to be pooled across imputed data sets in a way that accounts for uncertainty in the imputation. Now, one critical point I wanted to make regarding multiple imputation is what variables you should use in the imputation model, right? So the common consensus for doing an imputation is you want to make sure that all the variables you are including in your main model of the outcome of interest should also included in the imputation model for the missing value. And also how the covariates are modeled in your main model should also be the same setup for the imputation model. For example, if you wanted to study interaction between some covariates in your main model, and make sure that you have that same interaction term included in the multiple imputation model in order to get unbiased inference for your main model. So now let's move on to the likelihood-based approach. So in this case, missing data is handled within the analysis model without, literally imputing the missing values or doing some kind of reweighting. Okay, so that's the idea of a likelihood-based approach. And underneath that, you have several choices. You have a maximum likelihood model, such as the conventional random effects models for longitudinal data. You can also do the so-called full information maximum likelihood approach if you are doing the structural equation modeling. And in the absence of the missing data, the maximum likelihood and the full maximum likelihood approach, for full information maximum likelihood approach is equivalent. So if you wanted to compare sort of the pros and the cons between the likelihood-based approach and the multiple imputation-based approach, it depends on how many, imputed values they're using for MI, and what is the validity of the distributional assumptions about your outcomes, and the amount of missing data, and also certainty about, the missing data prediction model. So what should go into the prediction model? All these things would matter, so there's no simple answer which one is better or worse. It's sort of depending on the situation. But if you have a large number of imputations, typically the two will give you similar results. And the other thing to point out, again, to emphasize is the key assumption underlying the likelihood approach, again, is the missing at random assumption. So now I'm going to move into the topic of sort of a longitudinal analysis. And here what you're seeing are the top 4 reasons for conducting longitudinal data analyses. Number 4 is to inform policy. So if the focus is on a population average, then one model that people typically use is called marginal models, or GE models, generalized estimating equation approach. If the goal is to study natural history at an individual level, you want to see how the individual trajectory of some kind of an outcome over time, then the focus is on the subject-specific trajectory or growth curve. So here we're talking about random effects models. By analyzing individual specific trajectories, and then once you have the individual specific trajectories, you can estimate population average trajectory by averaging the individual specific slopes, for example, if the trend line is linear. The second reason could be, if you want to make a prognosis, incorporating history. So in this case, we'll be talking about transition models, right? Or autoregressive or Markov models that can allow you to use, the values collected from previous visits at an individual level to predict the future values for the same individual, or for the groups of individuals sharing the same characteristics. And so this is talking about transition of health states. And the number one, reason for doing the longitudinal analysis is we hope that by doing the longitudinal analysis, it helps us to progress from association toward causal inference. So even in the case of the observational studies, there are special class of methods that you can use to try to do a causal inference based on the sort of analysis that you've done using the regular longitudinal analysis methods. For example, if you try to deal with the time varying confounding in your covariates in the observational study, that you need to look into marginal structural models for causal inference in the observational study situation. So now, population average models, right? So here I talked about, the different terminologies. Some people call them marginal models because you're focusing on population averages. Others call them GE models or panel analyses. Okay, so these are sort of talking about the same thing. And the purposes of using these kind of models is to, wanted to make an inference about a population average. And we in this case, the within person correlation becomes a nuisance. We just wanted to account for the within person correlation over time without making explicit inference on a correlation structure. And we wanted to get a robust inference, right, by analyzing the longitudinal data using GE, for example, to get robust estimates of the standard errors that account for the within person correlation. On the other hand, if you talk about the subject-specific models, and these are the different terminologies used in the research community, sometimes it's called mixed effects of growth curve models, multi-level models, and hierarchical models, or random effects models. Probably random effects model is the most common terminology. So here the purpose is to focus specifically on individual trajectories, want to see how the individual trajectory deviates from a population average. So in that sense, we are interested in analyzing between person heterogeneity, or have to quantify the degree of a between person heterogeneity. And there are important assumptions to be made underlying the random effects models. So I'll talk about it in a minute. So here's looking at a sort of a graphical comparison between the population average approach and the subject-specific approach. So here we're looking at just the outcome Y, and the predictor variable is just the time since baseline. So you see the dots. Those dots represent individual observations. And if you're doing the population average approach, you're basically doing a cross-sectional calculation of a mean at each time point, and basically just connect the time-specific group averages to form the population average trajectory. So in other words, you're ignoring, the individual level data, right? You don't make a distinction that, which of these points belong to the same individual. So if you're doing a subject-specific analysis on the right, then what the analysis model does is to try to fit the individual specific trend line. One for each person, right? Each person contributes a pair of observations in this example. So you can fit a trend line at the individual level. Then in order to get a population average line, you just take the average of the slopes. So basically that's what the specific effects model, subject-specific effects model is trying to do. And those individual lines is called random effects. So it's a deviation from the population average in the middle. Okay, so just in summary, the population average approach, you're looking at the slope of the averages, whereas if you look at a subject-specific analysis, you're looking at average of the slopes. And the two are equivalent under these assumptions. If the goal is to try to get at the population average, the two will give you the same answer if the data are normally distributed, for example. If the within-person correlation is correctly modeled, and if there's no missing data. Of course, that does not happen very often in reality. So population average model fitting, depending on which software you use, you can use a JHAD-RCMAR, in SAS, you can use an SPSS or Stata, XTGE to fit a GE model. And both, regardless whether you use a likelihood-based approach or using the GE approach, and both will give you accurate parameter estimates, whether or not the correlation structure is correct. So, regardless of how you specify the within-person correlation over time, but both approaches will give you the precise, accurate estimates. But the standard errors will be incorrect, if using a likelihood approach, but the correlation structure is not correctly modeled. In comparison, if you're doing a GE approach, the inference, the calculation of standard errors tends to be more robust, regardless of, whether the correlation is misspecified. Packages to fit a random effects model. So here you can use, again, a list of different programs you can use. And in the interest of time, let's move on to the longitudinal data scenario. So here I wanted to just refresh the idea and the definitions of the three missing data mechanisms, but this time is in the case of a longitudinal data analysis. So missing completely at random in the longitudinal data scenario means that a dropout time is random. So that dropout time, the length of follow-up, as in this graph, is indicated by the lines. Each line represents each individual. You see the length of follow-up varies across individuals. That length is somehow occurs in a random fashion. So that's called missing completely at random. If the goal is to estimate change in the population average level of disability with age, as in this example, and you have two choices. You can do the GE, focusing on the slopes of the averages, or you can do, in this case, will be represented by this red curve if you're doing the GE. Or you can do in the random effects models by taking the average of the slopes. You fit the individual slopes and then you average these slopes to get the population average curve. So in both cases, you'll get an unbiased population average trajectory. So the next scenario is if you are looking at an MAR scenario. So in this case, you see that as this graph illustrates, the length of follow-up is actually a function of physical disability on the y-axis, right? You see the follow-up time is shorter when the disability score is, or the level of disability is higher. So this means that the likelihood of missing data or study attrition is a function of the observed physical disability value. So now, if you look at still the same two approaches, if you do the slope of the averages approach, which is a GE approach, basically, again, you're ignoring the individual curves. And if you take the average of the data points, ignoring the individual trajectory, then you get a biased inference. In this case, it's represented by the green curve. The red curve is the truth. The green curve is the biased trend line. Now, if you do the random effects model, in this case, again, you'll be fitting the individual specific trajectories. Then if you take the average of the slopes, you'll get an unbiased inference under MAR scenario. So now the last, which is the most challenging case, again, is called a missing not at random. So here you see that the trajectories, the length of follow-up cannot be predicted by the level of physical disability. For both high and low physical disability, you can have a shorter versus a longer follow-up time. So now, what if that the red dots on the screen now represents the unobserved missing values of the physical disability score? Okay, so you did not observe them for the subset who dropped out early. So you know that their trajectories are characteristically different from those who stayed in the study throughout the study period. So now if you do either GE or the random effects, so they both will give you the biased estimates. So now, what can you do if you have a non-ignorable missing data mechanism situation? Well, the solution depends on the missing data pattern. You can have intermittent missingness, meaning that missing in one visit and then maybe return at a later visit. Or you can have a monotone missing data, right? Once they dropped out, they never return. And the methods for monotone missing data are well developed. So under that category, you have three choices. So you have a selection model, had a mixture model, or frailty models. I mean, we don't have time to get into each of these different approaches, but I just want to briefly mention that if you are thinking about a selection model, basically you are modeling both the missing data mechanism and your main model in one step. So you have a sort of a combination of a likelihood of functions. One is for missing data, one is for your primary outcome. If you're talking about a pattern mixture modeling, then you're talking about a stratified approach by the missing data patterns. So that's the pattern mixture model. The frailty model is basically a latent variable approach. So you're making an assumption there's an underlying latent variable, maybe it's impacting both the likelihood of missing data, but also the study outcome. So you wanted to account for sort of the shared variance because of the underlying latent variables. So if you have a non-ignorable missing data scenario, so it is important that to make sure that you'll have to model the missing data mechanism one way or the other. And in order to do that, it requires very good prior knowledge about the nature of missing data process. Okay, so you have to draw information from other studies, similar studies looking at the similar outcomes. I mean, whether they provide you additional information about, the likelihood of missing data under different scenarios. So now here I want to draw your attention to this National Academy report on missing data. So you click on the link, you can download the book, the ebook. It has a wealth of information for how to handle missing data in clinical trials. Okay, so it's a very comprehensive summary of different missing data methods. If you are running a clinical trial with missing data as a possible scenario. And I mean, previously I talked about, importance of auxiliary covariates, so if that's something that you can collect in your study, make sure that those covariates are related to not only to the reason for dropout, but also related to the outcome of interest. The goal of the different missing data approaches is to make the MAR assumption as tenable as possible, after accounting for the auxiliary covariates. So that's the goal. So you wanted to do everything that you can to mimic the missing at random assumption. Of course, I mean, you'll never have a definitive conclusion about whether a particular scenario is missing at random, but you need to try to incorporate all the information you have in order to maximize the likelihood of the MAR assumption. So in summary, I think the number one most important thing for you is to try your best not to have missing data. That means that you have to design strategies at a study design stage to prevent and minimize missing data. If you have missing data, then you need to understand that missing data can lead to loss of power and may yield a biased inference. And all the models you use make some assumptions about the missing data mechanism. So understanding the assumptions is very important for data analysis. And also you want to make sure that the observed information cannot help you distinguish missing at random versus missing not at random. So you'll have to make some assumptions in order to see the impact of different assumptions on the statistical inference. So that's where the sensitivity analysis becomes very important. All the statistical default methods that we use routinely, logistic regression, including survival analyses, linear regression analyses, all those are give you valid results only under the assumption of missing completely at random. Okay, so that's important to keep in mind. And multiple imputation is certainly it's very popular, particularly for complex models where the likelihood approach may not be that easy to adapt to the missing data scenario. So multiple imputation becomes a straightforward, relatively speaking, a straightforward approach. And with that, I mean, I'm happy to answer any questions you may have. Thank you.
That was a good review.
Oh, thank you.
Yeah, there's one question in the chat. I don't know if you saw it.
I cannot see it.
Oh,
Um,
I'll ask from Amal. Can you speak to the difference between REML and ML in the likelihood-based
Yeah,
approach?
good question. And the difference between REML and ML, REML is designed to get a correct inference on the standard errors of random effects, variance covariance matrices particularly, and so that's what REML is designed for. So in other words, if you're just doing the regular ML, when you're feeding random effects models, the estimates you're getting for the variance covariance matrix for the random effects tend to be biased. So you need to have some kind of a correction, for the estimation of variance covariance. But if you're doing the REML, so you're paying a price in the situation where there's a lot of missing data. So there's a trade-off, right? If it happens to choose between, you have to choose between the two, then I would say that, it really depends on whether you are in the missing data scenario or not, and how much missing data in your analysis.
Great, thank you. Gail, did you have a question for Chenley?
Yes, this was a wonderful study. I've had this question for years, and I just assumed that I knew the answer, but I want to ask now because your presentation may speak to it, and you may have already addressed this.
Mhm.
So I've always assumed that multiple imputation and sensitivity analysis is like a sound resolution or way to deal with missing data, but and I guess a problem occurred where I was thinking, how should researchers address questionnaires or scale measures with missing items? So you talked about random versus non-random. So let's say they have several scales and they say, wow, there are some missing items that are not random. These are non-random. Maybe they are situated along a certain pattern. Let's say, I know the common one is like missing income is something that we usually find. So my question is that if questionnaires are missing non-random items, but the participants are still part of the study, it's just that they have missing data, how significant could these methodological problems be, or what, if any, problems these could present? Like when do they become a problem, when the researcher needs to say, I've got to figure out something beyond multiple imputation or sensitivity analyses?
Yeah, I mean, I guess the most important underlying assumption for missing imputation approach is, you don't get to observe everything that you wanted to observe for everybody in your study, right? So that's why you have missing data. But you're also making the assumption that, for those who you actually do have data on them, they can represent, the ones that you actually missed for one reason or the other. So in other words, I mean, you can, as long as in your data set, there's a subset of people, I mean, no matter how small that subset is, can still represent the people that you did not observe. So that's going to be the critical assumption. But it's hard to tell whether that's the scenario, right? That's the reality in a one particular study, right? So you will never have a definitive answer. So that's why representative sampling is important, right? For any statistical analyses. So that's my answer to the first question about, when you think the multiple imputation is a valid approach. Now, on the second part of the question about sensitivity analyses, typically people do sensitivity analyses is when you are uncertain about what is the underlying reason for missing data. So it's more in the arena of having a missing not at random scenario, right? So there, that, part of that reason that someone did not show up maybe is due to this or that reason, but I'm not entirely sure. So that's where the sensitivity analysis has a value. So now you have to imagine the different possibilities, right? You don't entirely rely on observe the data to make those assumptions. You have to make up scenarios. Well, of course, I mean, those scenarios has to be somewhat, the possibility, right, could happen in real life, even though that you did not have those scenarios represented in your population. But they may, occur in another different study setting, right? So now that's where the sensitivity analysis comes in, depending on how you make those assumptions and the scenarios.
Thank you so much. That was excellent. Thank you.
I see George and Harry.
Go ahead, Harry. Go ahead.
Thank you, George. Can everyone hear me, by the way?
Yes.
Okay, great. So thank you so much for a very helpful and informative presentation. Do you have any favorite resources for anyone trying to learn more about longitudinal analyses, missing data analyses, and then combining missing data and longitudinal? Because I've been trying to do this for a little bit, and part of the issue I find is there's so much literature out there, but sometimes it's so far advanced that it's hard to fully comprehend when we are trying to learn it for the first time.
Yeah. I mean, I do have I can share my slides. So these are the references. I mean, some of them are more technical, others are less technical. But I also included, you see the blue shaded, I mean, blue font links. So those are the useful applications for fitting the different types of models, like random effects models or GE models. I mean, depending on what is the software that you use, SAS or Stata or SPSS. So those will give you good references or examples of how the different models can be run.
That'll be super helpful.
Yeah, so happy to share these slides with you.
Yeah, that'll be incredibly helpful, actually. And my last question very quickly is, I use multiple imputation for cross-sectional studies a lot. And do you have any recommendations for how many data sets you should impute? So I've heard anywhere from, I usually do about 20, but I've heard anywhere from 5 to 100. Do you have any personal recommendations?
Yeah, typically, I mean, I think 20 is plenty. For most scenarios, I mean, I think most people use maybe even less than 20, 10, but it also depends on how complex the model is, right? The more complex the model, the maybe the more samples you need to replicate, you need to produce. But
Thank
20
you.
is I think it's good enough in most scenarios.
Thank you so much.
Yeah, sure. Welcome. George?
Yeah, thanks, Chinley. I know we're almost out of time here, but thanks for a terrific talk. And I have a question. I think it's somewhat related to Harry's question. You pointed out early on in your talk that we moved a long way from just simply ignoring missing data and doing list-wise deletion of missing cases. And we've got all these very sophisticated methods right now, like multiple imputation and maximum likelihood and likelihood-based approaches. And so I was just wondering what your impression is of the amount of error connected with the use of these different techniques. Even if you choose the most appropriate technique, I mean, there have been studies done of like power analyses in scientific reports that we know people misuse power analyses and do it incorrectly. And I'm wondering, what's your sense? I'm sure you've served as a reviewer of many, many papers and have weighed in on, these methods, but, are most people using them appropriately now? Have they been around long enough that people know what they're doing? Is there still a lot of error connected with using these methods, and it sort of seeps into the literature?
Yeah. I mean, that's a good question. I mean, my understanding or my observation is still it certainly has improved over the years. I mean, given that there are articles published targeting the users, right, and non-statistician groups, and so I think the overall it has improved, but I still see sort of misuse in published applications. I mean, for sure. And the other thing is probably most underutilized is in a power calculation. I mean, I rarely see, in the research proposals where, I mean, that there's going to be missing data, but the power calculation pretty much ignores it. Or doing a very simple thing. For example, if I did a calculation of 100 people, then I just inflate it by 20%, and that becomes my sample size. But for simple analyses, maybe that's good enough, but for like a more complicated modeling approaches, that's certainly not sufficient.
Thank you. Talks like this really help address that problem. So thank you very much.
Simulation is becoming, more popular. If you wanted to do a power calculation using a data simulation, I mean, it's easy. It's not that difficult to do. I mean, of course, it takes extra effort, but it's going to create a lot more realistic data scenarios. So you have a much better idea of the impact on the statistical inference. I think time is up. Thank you so much. Yeah, and we can make the recording and the slides available to you. I guess Veronica, we can post them at the website, correct?
Or we can post them, and we can also send them out.
Yeah, thank you.